be talking on. So have you? He has not given a title. So have you shared your slide, Subimal?
Uh,
Will you please
Let
share
me
your slide?
share. Yeah, I'll do that.
Yeah. So I will hand it over to Subimal, please. You may please take over.
Are my slides visible?
Yes, visible. You make it full
Okay.
screen.
Yeah, I'll do that. Right. So thank you, thank you, Professor Ghosh. It's nice to be back to QIQT speaking about our work. So today I'll be talking about the variation of self-imaging distance in waveguides. I had spoken on a similar topic in the previous QIQT, and today I'll be presenting a few new results towards that. So to begin with, we begin with the Talbot effect, which started with the discovery of Henry Fox Talbot in 1836, which is a very, very long time from now, close to about 180 years or more. In 1836, what Henry Fox Talbot did was he took a grating that was prepared by Fraunhofer and looked at light transmitted across it. And when he saw the transmitted light through a lens, he had focused the lens on the grating and then gradually moved the lens away. And what he found was alternating bands of colors that showed the image of the grating. And that is very nicely given in this paragraph. This is an excerpt from his paper. The citation is given on top. And he says that what he observed through the lens, he said that the appearance was very curious, being a regular alteration of numerous lines or bands. Numerous lines or bands of red and green color having the direction parallel to the lines of the grating. So he was seeing the image of the grating in different wavelengths as he moved the lens away. And it turned out that with red and green, he observed a set of images. He moved it further away. Then he saw images appear in blue and yellow. He moved it further away. It again became red and green. And this continued as he kept on moving the lens away from the grating. It happened repeatedly. So this was a very interesting thing to be seen. And the images and the image of the grating observed through the lens was very clear. This came to be known as the Talbot effect. And it has been used since then for a number of applications. But if you see the picture in the middle, which shows a simulation of the near field image across the grating at the distance ZT on top. The grating is at the bottom. It is being illuminated by light from below, monochromatic light of wavelength lambda at about 8,000 wavelengths. You see the image of the grating being produced perfectly. So that distance is marked by ZT, and it is now called the Talbot distance. The expression for the Talbot distance was given by Lord Rayleigh in 1881. He gave two expressions for it, a quite accurate expression for the Talbot distance, which is lambda by 1 over square root of 1 minus lambda square by d square, where d is the grating element. An approximation of this expression leads us to 2d square over lambda. Very easy to see that you can arrive at 2d square over lambda. And this Talbot distance has often been used when while studying self-imaging across different kinds of gratings. And a very related expression comes out when one observes the propagation of beams through waveguides as well. Now, we are going to look at what happens when light is injected in a waveguide, how it propagates and produces a beautiful carpet like the one you see over here. Here, the carpet is in free space, but what we are going to see is in a waveguide, a confined space which will confine light only within the boundaries of the waveguide. Now, what happens in a waveguide? In a waveguide, you have the confining walls. To put things in perspective, we have a waveguide with a gap of 2a between the walls. The wave propagates along the z-axis, or the axis of the waveguide. X is the transverse direction, and when you inject a beam, it'll propagate and produce a beautiful carpet like the one you see over here in yellow, the intensity carpet. And at a certain distance, which is marked as 1 in units of L, which is 4a square over lambda, it becomes, the input beam is reproduced. Now, so far, for almost all the works that have been published, people have looked at a paraxial form of waveguide propagation. So what happens in the paraxial form? In the expressions that I've given below, we have looked at a waveguide with metallic walls. So you have the wave propagating only between the walls of the waveguide. You do not have any part of the wave beyond the boundaries of the waveguide. So and the modes, they can simply be written down as harmonic functions, normalized harmonic functions, sines and cosines. The propagation constant. So what is this propagation constant? If you inject a beam, through the waveguide, it'll propagate through the waveguide as a superposition of its modes, that is the profiles that move without any distortion through the waveguide. They are the modes of the waveguide. They are the EMs. So you have EM, and each of them a certain proportion, a weight factor AM, a certain proportion of that would be propagating through the waveguide. And as it propagates, each of these modes will collect a phase. Each mode collects a different phase. It turns out that if you have the width of the waveguide much larger than the wavelength being used, then the phase that is being collected is proportional to the square of the mode index m. So the mth mode will collect a phase which is proportional to m square. And the propagation constant also approximately becomes proportional to m square. I say that it is approximate because an accurate expression would give you a square root of the term in brackets, this 1 minus m square lambda square by 16a square. You wouldn't have the half term. And this leads to a very beautiful carpet, and you will have a perfect reproduction of the input field at this revival distance, which is L, or 4a square over lambda, a being half the guide. So to put the study of self-imaging in context of this conference of QIQT, or even the use or with quantum technologies, I'll cite this relatively recent PRA paper by Erickson et al., who used studied Talbot self-imaging, and they observed this 2-photon interference in ring core fibers. They are so the core of the fibers are like rings. If you take a cross section, the core is a ring an annular region with a high refractive index. The central part is low refractive index, and outside the ring, you again have a low refractive index. I'll just show a figure from their paper, and what they had done is they injected light in the core, at one edge of the core, and as it propagates, it produces a beautiful Talbot carpet, and at the Talbot distance, you get a beautiful reproduction of the field. And what have they used it for? They have shown that it can be used as a very high quality beam splitter. They have observed a 2-photon interference, and they have also pointed out that this can have numerous applications, not only as beam splitters, as couplers, as beam multiplexers, for quantum information processing, and a lot of other things. A lot of avenues actually open up if one can exploit self-imaging. So with that, with the context in place, we move on to take a look at another important concept over here, which is quite well known to a lot of our participants. That is the concept of paraxial and non-paraxial propagation. So when you have a Gaussian beam and you let it propagate in free space, it would technically, it should diverge. Now, how divergent would the beam be? The divergence actually depends on the ratio of the beam waist to the wavelength. So the beam waist is the smallest width of the waveguide. Of the Gaussian beam when you eject it out of the source. As it propagates in free space, it will spread out. The black lines, the black dotted lines here, will mark the spot size. So if you place a screen at a given Z, the spot size that you would observe would roughly be given by the edges of the wherever the black lines intersect the plane along a particular value of Z. So as you move from right to left, you are decreasing the spot size of the beam. I have kept the wavelength fixed. And for a larger beam waist, you see that the tensile of light is quite collimated. It is parallel to itself. It is parallel to the axis of propagation. But as you keep on decreasing the beam waist, the spot size increases very fast as the beam propagates in a free space. So on the left, you will have a non-paraxial beam. On the right, you have a paraxial beam. This was quantitatively studied by Nemoto in 1990, and he kind of quantified a beam to be paraxial or non-paraxial depending on the beam waist. So if you have a beam of width lambda, of wavelength lambda, then K would be the wave number, and if W0 is the beam waist, then a value of KW0 larger than 4 would give you a paraxial beam. A value of KW0 less than 1 would be a completely non-paraxial beam. In between, you have two transition regions, which I'll not explain too much now because we will not be needing it towards our talk, but it's a very good paper to read. So let's move on to a very simple waveguide system. The case of a waveguide with metallic walls, very easy to study analytically also, at least partially. So what I have done here is I've taken a waveguide with metallic walls, injected a Gaussian beam, a normalized Gaussian, the expression I've written down below. I inject a Gaussian beam, and that will excite the modes in the waveguide, a finite number of them. You will have a cutoff frequency, so a finite number of them will be excited, and each of them will propagate with a propagation constant beta n. The beta n's can be calculated very easily. as they propagate at the self-imaging distance capital L, which happens to be twice the talco distance, roughly, it will produce the input field with an overall phase. So that would be a perfect self-imaging. Now, I call this, I put this cautionary note here because we are looking at self-imaging, which may or may not be perfect. It would be perfect self-imaging if we are looking at this propagation in the paraxial domain. But today, we will be seeing what happens if you have a non-paraxial beam propagating in a waveguide. There are a few things I would also like to tell you at this point. The coupling coefficients will depend on three factors. It will depend on the width of the waveguide. From the previous slide, there is one small difference here. In the previous slide, we had a waveguide width of 2a. Here, I've taken the waveguide width as a. So the limits are minus a by 2 to plus a by 2 for the waveguide. So the coupling coefficients depend on the waveguide width of the input beam, and the offset, whether you inject it in the middle or slightly away from the center of the waveguide. All these three factors, they contribute to this coefficient, and they can be calculated analytically also. At this point, I'll also tell you that if you have a symmetric input, like a Gaussian beam injected perfectly at the center, you'll have the revival distance as twice of ZT. If it is a perfectly antisymmetric input, it'll revive at twice the revival distance for the symmetric input, and at 8 times if you have an asymmetric input. So these values are hold very well if you have a paraxial beam, but they will change slightly if you move on to the non-paraxial domain. So what do we have here? We have two parameters. One parameter is the width of the beam. So we can make the beam thinner or broader. And the other parameter is the offset, x0. So we have two free parameters here to see what happens to the self-imaging distance. It is expected that as you change the width of the beam, the coupling coefficients are going to, the coupling coefficients will change, and the self-imaging distance thereby is also going to change. That is expected. And that means that if you put a detector or an imaging plane, or if this just forms a part of your optical system, then you need to know exactly where this self-image is formed so that you can have a very efficient coupling into the next element. And if you are using a non-paraxial input, which could be because you are using, you're injecting the beam through a thin fiber, you could end up with a non-paraxial propagation of the beam in the waveguide. And these expressions for the revival distance would hold true only approximately. We can use them only as a guide to find out where it will revive. To analyze this, we took the scalar wave equation. And the first thing that comes to the mind is, in the scalar wave equation, we have the material parameters for the waveguide. So if we analyze, if we make any studies with this waveguide, come to any conclusions, would they be dependent on the material parameters? To make it independent of the material parameters, we just make a single transformation. All the lengths, all the spatial coordinates and the lengths in our system are scaled up by this factor of k0 times n1. So you multiply k0 n1 to all the lengths, and this equation transforms into another equation where you do not have an explicit dependence on the material parameters, and that is what we will take a look at. So now comes the question of, how do we find out the self-imaging distance? If you have looked at the previous expression, we find out Ez. Ez is the field profile at a distance z. one can have an analytical expression for Cn. Didn't write it here to cram the slides with a lot of mathematics, but it can be very easily calculated. And then you can calculate the beta ends, find out Ez, and find out the field profile at any arbitrary Z. So you find out, you fix the point of injection x0, look at the intensity along Z, and see where you are going to have a revival of this field. So what happens in this case is you're going to get a maxima which is close enough to the input. I say close enough because it would be perfectly self-imaged if you have a paraxial beam. In the case of non-paraxial beam, if you excite the higher order mode, some of them might leak out, and you may get an input which is slightly less intense than an output which is slightly less intense than the input. So you find out the intensity along the line of injection, and you will find close to twice ZT a local maxima. We find the position of the local maxima numerically because we have the analytical expressions for it. And then we change and we find that that peak in the intensity by varying the two independent parameters that we now have, the width of the Gaussian beam and the offset of the Gaussian beam. So in this particular case, I injected the Gaussian beam right at the center and then found out the self-imaging distance. So when I do that, I find that when it is injected right at the center, x0 is 0, I get a variation of the self-imaging distance, which is not very high. If you take a look at the values on the y-axis, it doesn't look very high, but do remember that it is scaled. It is scaled by the Talbot distance, which happens to be around 10,000. And 10,000 in units of lambda, of course. And the curve in blue shows a variation of the self-imaging distance with the width of the input beam. The width of the input beam has been scaled by the width of the fundamental mode. The fundamental mode is a cosine. It's half the cosine function from 0 to pi. So WF is the full width at half maxima for that cosine, and you get a curve which shows a smooth variation. It goes up and it shows another variation, kind of saturates as you move on to a higher width. We do not make it a very, very broad beam so that we can keep the beam well confined within the waveguide. I'll also point out here that the error bars have also been plotted, but you don't see it because the numerical errors are 1 in 10 to the power 5. So that tells us that we have the smoothness of the curve, and the low errors tell us that we are not looking at any numerical artifact. But and the other two curves, the orange and the green ones, they are produced by using a beam that is slightly offset. So you offset the beam by 0.5% of the waveguide's width, a little to the right, a little more to the right, where when you offset it by 1% of the waveguide width, you would get the green curve. The green curve shows a slightly different variation. The blue and the orange ones, they move almost parallel to each other, but the green one shows a typically different behavior. We do not move it too far away so that we do not excite too many of the higher order modes. But this does reveal something interesting at these three places. I have marked the three regions, in red, blue, and green, and it kind of looks that we have the curves crossing each other. And what would that mean? It would mean that irrespective of the offset, the self-imaging distance remains the same. And when that happens, that means that we can use this system very efficiently if we know what beam width to use and exactly where we are going to get such a self-imaging, such a fine-tuned self-imaging distance where the self-imaging plane becomes almost stationary with respect to the offset. And that is important because it might be very, very difficult to launch a beam right at the center of a thin waveguide. So now let us take a very close look at these plots. I have expanded those regions of the plots in three insets. If you see carefully, the region marked in red and the region marked in green, the curves, they cross, but they do not cross exactly at the same point. But the region in blue, they cross exactly at the same point. And that is a very, very interesting and important result. So the self-imaging plane is very robust to the offset for a certain width of the Gaussian input. Now this is something that happens in a waveguide with metallic walls. In fact, these other two regions are not really very bad, although they do not cross exactly at the same point, but the crossing happens at a very in a very small window of the waveguide width, and the self-imaging distance also varies very, very little. So keeping that in mind, we will take a look at a different waveguide system. Now, is this result unique to this waveguide with metallic boundaries, or it happens in other kinds of waveguides as well? So we'll take a look at the one-dimensional parabolic index waveguides, the graded index fiber or graded index slab waveguides to be specific. The reason I have chosen these two is because the modes and the eigen and the propagation constants can be found out very easily in closed form. It turns out, and by the way, they both have got very nice properties. The first one with metallic boundaries makes it easy to fabricate. The second one with the parabolic index parabolic index profile has a very strong confining property. It doesn't let light leak out from the waveguide very easily. So we do the same thing. I have put up the expression for the refractive index. You see that the square of the refractive index would be like a parabola. And we make the same transformation for this for the scalar wave equation to make it explicitly independent of material parameters. At this point, we note that it has got a one-to-one correspondence with the harmonic oscillator problem, the quantum harmonic oscillator problem, and therefore we derive the results for the eigenvalues, or the eigenmodes, and the propagation constants by mapping the corresponding quantities from the results in the quantum harmonic oscillator. It can also be done in any other way, but we have introduced this quantity alpha square, and square root of 1 minus alpha square x square will give me the refractive index profile. I'll come back to this in a while. Now let's move on to the next part to appreciate what happens in a parabolic index fiber or parabolic index waveguide, not a fiber. It's a slab waveguide. I have a set of 9 images over here in this 3 by 3 grid. If you go from left to right, you are changing the offset of the input Gaussian beam. With the one on the extreme left, the beam is injected right at the center. On the extreme right, it has gone very close to the boundaries. As you come down along any column, the width of the input beam has increased. Now, as you increase the width of the input beam, you can see that the beam propagates undistorted and in the lowest figure. And that is so because the input Gaussian beam will completely couple only to the lowest order mode. And you do not excite any other higher order mode, and therefore it propagates undistorted. The other thing that I would like to point out at this point, we'll look at the other two figures on the left side. How different is this from the previous waveguide? The mode profiles smoothly die out, remaining confined within the walls of the waveguide. The second thing that I would be pointing out over here, it is not a difference, but I would point out over here that by using the scaled version of the variables, the maximum value of this refractive index profile, which is square root of 1 minus alpha square minus x square, has a maximum value of 1, and the lower bound will decide how many guided modes you can have. Below the guided modes, you will have a continuum of radiation modes, which, if excited, will cause a leakage of the input beam out into the cladding, and only the guided modes will continue to propagate inside the waveguide. If you change the material parameters, you get another set. Of a refractive index profile, which I have shown in red. So, and the corresponding propagation constants, or rather squares of the propagation constants, I have shown here in red horizontal lines on the right half of this figure. Below this lowest part, you have this red shaded region, which is the continuum of the radiation modes. So we will confine ourselves only to the guided modes. Anything, if one excites the radiation modes, it will leak out. Now let's come back to this 3 by 3 grid of propagating beams inside the parabolic index waveguide. If you notice carefully, as you change the offset, the place where the beam is reproduced changes very slightly. On the extreme right, the revival distance is a little smaller than the ones on the extreme left. So that led us to take a look. That led us to take a look at the dependence of the same kind of study, the dependence of the self-imaging distance with the width of the waveguide and the offset. Now, how did we do that? We injected a normalized Gaussian into the parabolic index fiber, or a parabolic index waveguide. I'm sorry, it's not a fiber. And we looked at the intensity variation along the axis of injection, which is this vertical gray line. At roughly the revival distance, shown by this green dashed line, we have the self-imaging that is occurring, but we have to locate the self-imaging plane only by using numerics. We do not, as of now, I do not have a way of doing it analytically. But as far as these amplitude coupling coefficients are concerned, one can work out an expression for them if you use a Gaussian as an input. And that expression I have written down on the right. It can be worked out, not very difficult to work out. It's just a little lengthy. There's one thing that I would like to mention over here. I have also made one assumption that I am injecting the Gaussian beam exactly at its waist. It's not being injected away from this input. Now I do that to make the calculations a little simpler. So the expression for the uh, Gaussian input profile does not have the radius of curvature or the Gauss phase in it, because this would be the beam profile at z equal to 0. To give to give a clue of how the amplitude coefficients vary, I have plotted this the magnitude of Cm, or the magnitudes of the input profile for a beam injected at the center. So x0 is 0. So beam is injected at the center, and for that I'd go back to the previous figure. So we are looking at this set of figures on the left column of this 3x3 grid. X0 is 0 in all of these three. And how do the coefficients change as you change the width of the waveguide? As you keep on increasing the waveguide, the beam width from 0 to a higher value, you see that the higher order modes, they fall in their contribution, and all of them go off when you have a beam width which equals the width of the fundamental mode, and that is something that is expected. So what we find here is that the coefficients, the expression of the coefficients, they reflect uh, the physical description of the system. To be extra sure, we also found out these coefficients by an independent finite difference calculation of the scalar wave equation. And if you see carefully, the curves that I have shown here have got are in two sets. One set of curves are in color, and the other set of curves are dashed black lines. So the dashed black lines are the ones which are numerically simulated using finite differences for the scalar wave equation, and they agree very, very well with the analytical expression. So that gives us a kind of confidence that we are doing things right. I have not shown an exemplary curve for a non-zero offset, because it would vary very, very fast, and very difficult to explain how it would change. It would just depend on what is the width of the waveguide, how many modes you're exciting, which ones you're exciting, and so on. So for this centrally fed input, it looks quite well. And here is a study of the self-imaging distance. And the self-imaging distance over here shows a nice variation as a function of the input beam width. Now, if to see this plot, we have a set of 6 curves, and 3 of them belong to the waveguide with one set of parameters, and 3 of them to another waveguide with another set of material parameters. So in this case, this parameter, the extra parameter that we get here is alpha. It depends on the ratio of the core and cladding indices, and that decides the kind of propagation that will take place in the waveguide. So you have this blue, orange, and green curves. The group of 3 curves at the bottom of the inset, they belong to the first waveguide, and they belong to 3 different offsets. One is for a 0 offset, which is the blue curve. The one 0 is for the blue curve, for the 0 offset. The orange and green are for 2 different offsets. The same thing is done for a second waveguide also. And we see that for each waveguide, irrespective of irrespective of the offset, the curves cross each other exactly at a fixed value of the input beam width, which is roughly around 0.76 times the fundamental mode width. So this, which we can call the magic width, is quite different from the self-imaging distance. Well, it is different. The difference is clear in this graph, but when it comes to actual measurements, the difference is about a few microns. Depending on, of course, the wavelength and the other material parameters, the percentage difference is not that high, but it's quite distinct. The partial expression for the self-imaging distance can be shown to be roughly about 2 pi by alpha, where alpha is a measure of the numerical aperture. I've shown it in a previous slide over there. It depends on the wavelength, the waveguide width, and the core and cladding refractive indices. So, and a corrected version, which is slightly different from this version, with a factor of square root of 1 minus alpha, they are way above the corrected version actually happens to be very close to twice the Talbot width. And for the paraxial case, of course. And here we see that this magic width of 0.76 times the fundamental mode width is true for any waveguide with a parabolic index profile. At 0.76 times the fundamental mode width, you will find that the self-imaging plane becomes stationary irrespective of the offset of the input beam. It is just that the self-imaging distance might be different depending on the material parameters. So this was an interesting find which we reported in our recent paper, and I have shown these two sets of curves because to be sure that this magic width of 0.76 is not an artifact of, or not a case of the material parameters that we chose for the first waveguide. It happens for any waveguide that you would choose, because we rescaled that equation. So here we have a few. I've almost come to the end of my talk. So here we have a few things to note. I'll quickly go over to the conclusion. And what are our observations here? The self-imaging distance is expected to depend on the width of the input beam and the offset of the input beam. And that is quite natural, because that would decide how many modes you're exciting, both these parameters. But our observation, which is interesting here, is that the self-imaging plane, the distance where the self-imaging plane is produced, becomes robust, or rather almost stationary for the offset of the input beam. You move the offset a little away from the center, the self-imaging plane doesn't change at all. But one must keep in mind that you do not make the offset too much, because one would then excite the higher order modes only. So we keep the offset close enough so that we do not excite too many of the higher order modes, and we find that the self-imaging plane remains stationary at a fixed value of the for the input beam width. The second thing is that this feature has been tested for two waveguides, for two different kinds of waveguides with completely different refractive index profiles. This feature is independent of the material parameters, which is very important, and it works beyond the paraxial regime. And why I say this works beyond the paraxial regime, because we can squeeze the Gaussian beam enough to make it non-paraxial. And although this result actually happens to fall in the paraxial regime, but you do get, at least for the case of waveguide with metallic walls, you get a region in the non-paraxial regime where you get an nearly stationary self-imaging plane. But we keep in mind that if we have a very thin input beam, we may not end up with a perfect self-imaging, because we would be exciting the higher order modes or even the radiation modes, causing a leakage of some of the energy of the input beam. So we will have a localization, but it will not produce a perfect self-imaging. Perfect self-imaging would happen when we are in the paraxial regime. This is something that we should keep in mind, and this should definitely be useful for designing very efficient optical connectors. Especially losses happen when you cascade optical elements, when you design an optical circuit or any optical setup, at least with waveguides and photonic circuits. It might also become very useful if one is placing detectors in front of these guiding channels. So it would be good to know where one would expect the photons to end up, and precisely that was done in that kind of a setup was used with the ring core waveguides. With that, I come to the end of my talk, and I would like to thank the DST for funding the QUEST project, of which I was a part earlier. A part of this work was done when I was a part of that project, and a part of it is being done here in C-Dac, and I thank C-Dac for the support as well. Thank you.
Thanks, Subimal. So now the session is open for questions. So if you have any questions, please unmute yourself and ask.
I have a comment. So
Yes,
may I
yes.
raise it? It is
Yes.
when you
Yes,
were
please.
talking, I was thinking about self-imaging requires paraxial regime. So I
Self-imaging.
was thinking, if you requires paraxial regime, in the paraxial regime, you would achieve self-imaging in a better way. So if I have a squeezed state, I am going out of the paraxial regime. So I was wondering, this is squeezed light is non-classical in the sense of our quantum continuous variable states. So would you say that self-imaging requires some kind of classical radiation in the sense of if you connect it with quantum? We make such comments.
I will not say so. I would say that perfect self-imaging requires paraxial requires a paraxial approximation. But what we get there, we do get a very good localization. But you can have waveguide arrangements where you do not lose out the photons, like the setup I just mentioned in the paper by Erickson. You have this ring core fiber, so the ends of the waveguide, they fold onto each other. So so as it propagates parallel to the surface of the waveguide, it folds back onto itself, and you could get good self-imaging in that case. Here we have boundaries which do not fold onto each other; rather they reflect light back. So the perfect self-imaging doesn't take place here at distances close to the estimated revival lengths in the case of
Mm.
paraxial regime, but perhaps it would take place at a much larger length. Because finally, if you see, the self-imaging distance is like a lower, lowest common multiple, an LCM of the propagation constants, or the phases rather. So there would be some distance where you get a perfect self-imaging, but it would not be at the distances where you would expect self-imaging for the paraxial case.
Okay, thank you.
I don't think I have answered you.
No, it's a just for curiosity, like many times we highlight a non-classical expectation, and it looked like
right.
it in that context, it would be good to know your comments. Very nice, interesting
Okay.
talk. Thank you.
Okay, thank you. Thank you.
Any other questions or comments? If not, then let's thank Dr. Subimal Deb again. And I think with this, we come to the conclusion to this session. And yeah, we thank all the speakers, the 3 speakers. It was really illuminating throughout the morning. So we'll join after lunch.